Section 1.4, Area and Perimeter. We'll see a lot of formulas in this section that I imagine you've seen before, so I might go kind of quickly through this one. But we'll be looking at two-dimensional and some three-dimensional geometric figures, and we'll talk about perimeter, area, volume, surface area. So starting in 2 dimensions, we're going to start with rectangles, which is kind of the most basic, in my view, two-dimensional polygon. So let's look at the formulas we have here. So the area of a rectangle is given by base times height. Okay, those are just the 2 dimensions of the rectangle. Okay, the base is the width and the height is the length. The perimeter can be found by doing 2 times the base plus 2 times the height. And that is just, if this is the base and that's a base and this is a height and this is a height, that's just the sum of 1, 2, 3, 4 sides, right? Which will be base plus base plus height. So that's where this formula comes from. Okay, already on to the next shape, parallelograms. Notice that any parallelogram could be redrawn as a rectangle. And as a reminder, a parallelogram is a polygon. It's a 4-sided polygon where the opposite side lengths are parallel to one another. Okay, so we have these 2 sets of parallel lines. And it turns out that a rectangle is actually an example of a parallelogram. It's a special parallelogram where all of the angles, all the interior angles are 90 degrees. Okay, but to come up with the formula for the area of a parallelogram, you can imagine just dropping a perpendicular. So we'll drop a perpendicular right here from one of the vertices down to the other side. Make it a right angle there. And we could just cut this triangle out and bring it around to the other side, and that'll perfectly fill in that space to create a rectangle. Okay, so in order to find the area of a parallelogram, we just need the length of the base and the length of this perpendicular that we drop down to make the same shape as a rectangle. Okay, so base times height is the formula for that one. Very simple example to get us started out. We want to find the area of this parallelogram right here. Okay, and we have that the base is 15 inches. Inches are the units we're working in here. And conveniently, we're given the length of this perpendicular right here. So the height of the triangle, or the length, the height is given at 8 inches. We won't always be given this length. Sometimes we'll be given this length, and we might have to use some facts about right triangles to find the actual height of the parallelogram, but this one's straightforward. So area is equal to base times height, and we're given that the base is 15 inches. Notice that I'm writing in the units, inches here, and we just want to multiply that times the height, which is 8 inches. Okay, and I will multiply these together, and I'll get 120. And for the units, I'm going to multiply inches times inches. Like this is multiplication all the way across, right? This is multiplication technically between the 15 and the inches and between the 8 and the inches, right? Because multiplication is sort of like the counting, like, okay, we're talking about inches here. How many of them? Like, what do we want to multiply inches by? We're multiplying by 8 to get 8 inches. So that's what I mean when I say this is multiplication all the way across this expression. So what's inches times inches? Inches squared. I'll put a box around that because that is my area. Okay, the units for any 2-dimensional polygon, if we're trying to find the area, will be inches squared. Okay, the second power is kind of what indicates that we're in 2-dimensional space. Okay, moving right along, triangles. Notice that if you place triangles side by side, with an identical triangle, it creates this parallelogram. So the formula for the area of a triangle is going to be half of the formula we have for a parallelogram, as this picture sort of indicates. So the area for a triangle is 1/2 base times height. Okay, and I want to sneak in a couple other formulas quickly. An alternative. So sometimes we don't have the base of a triangle, right? Because notice that in this picture, what we're looking at are right triangles. Okay, and we don't always have right triangles. Sometimes we'll have a scalene triangle. Let me just draw an example of what that looks like. Maybe it's something like this, where all 3 side lengths are different. In the case of a scalene triangle, in order to find the height, you would have to find the length of this perpendicular, or any of the perpendiculars that get dropped down to an opposing side. Okay, and that is not always feasible or convenient. So Heron's formula is another formula that we can use to find the area based on the side lengths of these 3 sides. So if this is our triangle, I'll call this side length A, this can be B, and this can be C. And what this formula tells us is we have to find S. Okay, so this is sort of this additional value that we need to compute in order to use this formula. S is 1/2 the sum of those 3 sides. So 1/2 times A plus B plus C. And then the area is given by the square root of that value S times S minus A times S minus B times S minus C. All of that being contained inside of this square root. All right, so not the nicest formula because we kind of have to do 2 computations. We have to find S and then use S in the formula, in the area formula. But sometimes this is easier than finding the height of the triangle. So we'll have that in our toolkit. And one last formula I want to sneak in. This is most likely familiar to you. The Pythagorean theorem tells us that for if ABC is a right triangle, this only applies to right triangles, then the length of the hypotenuse squared is equal to the sum of the squares of the lengths of the legs. A better way of saying that is just A squared plus B squared equals C squared, where A and B are the legs and C is the length of the hypotenuse. Okay, so those are our important formulas for triangles. Let's look at example 2. Suppose you want to plant a triangular plot of lawn in your front yard, and the dimensions are given below in this diagram here. If 1 bag of seed will cover 10 square feet, then how many bags of seed should you purchase in order to plant your lawn? So this comes down to finding the area that we actually want to cover with seed, and we'll have to do an additional computation at the end to figure out the number of bags of seed to buy. Okay, but let's start by finding the area. So let's find the area. And looking at this triangle, is this a right triangle? It doesn't look like it, okay? This is scalene. We've got these 3 different side lengths, 12, 18, 24. If you weren't sure and you wanted to check to make sure that this wasn't a right triangle, you could just look at the Pythagorean theorem and check, does 12 squared plus 18 squared equal 24 squared? You know, I can put a little question mark over this because we don't know. You could check that, and if you get equality, you know that you have a right triangle. If you don't, you know that you don't have a right triangle. Now, in this case, it turns out that it isn't a right triangle. So that tells us that this short side is not going to give us the height, or none of these side lengths are going to give us the height. So we're either going to use Heron's formula, or we're going to, drop a perpendicular and try and solve for the height. In this case, I think I want to use Heron's formula. So let's do it. I'm going to start by finding S. So, okay, we're using Heron's formula. And here's how we do it. So S is going to be equal to 1/2 times A plus B plus C, which in this case is 12 plus 18 plus 24. I'm not going to write out the units here. I'm just going to use the numerical values, and I know that at the end, since all these side lengths are given in terms of feet, my area is going to be feet squared, or square feet. So let's simplify this. I get 1/2 times 54. All right, and then dividing that by 2, 27 is what I'm getting for S. And now we'll plug into the actual formula. The area is equal to the square root of, I'm going to write this one out, S times S minus A times S minus B times S minus C. Okay, it doesn't matter, by the way, which of these three side lengths are A, B, and C. You can do it in any order. So let me plug in my values. This will be the square root of 27 times 27 minus 12 times 27 minus 18, and so on. Simplifying a little bit, this will be the square root of 27 times 15 times 9 times 3. All right, and using my calculator, multiply that out, take the square root. I get, and this is an approximation, I'm going to round this. I'll round this to, how about the nearest tenth? So I'm getting 104.57055, and there's some more beyond that. I'll just round this to 104.6. And what are my units here? This is an area, so it should be something squared. In this case, feet squared. All right, now we have the area. But we weren't just asked to find the area. The specific question is, if one bag of seed will cover 10 square feet, then how many bags do we need to purchase to plant this lawn? And to do this, we can do a bit of division. Okay, so how about last part right here? Let's find the number of bags. And to do this, we're going to have to do division, right? Because really the question here is like 10 feet squared times what? You know, times x is equal to, or I could even think of this as like, we want this to be greater than or equal to 104.6 feet squared. Right, I'm thinking of this as an inequality because we're talking about a number of bags here. I'm assuming that we're not going to be able to buy a fraction of a bag. So I just want to make sure that this is enough to cover this many square feet, right? So it just needs to be greater than or equal to 104 square feet. Okay, so solving for x here, I can divide both sides by 10 square feet. And a nice thing happens with the units here. So 104.6 feet squared, and if we divide that by 10 feet squared, notice that the units cancel out. Feet squared cancel with feet squared, right? Because anything divided by itself is 1. X has to be greater than or equal to, and then simplifying the numerical division here, 10.46. Okay, so we need 10.46 bags. That could be our answer. We could say that. But assuming that we have to purchase whole bags, I'll say 11 bags are required. Okay, so I'll list that as my answer. 11 bags are required. Okay, so nice little example of some Home Depot math there. Let's try another one. Example 3. In this one, we want to find a missing side length. So this actually isn't an area problem. This is just like, okay, let's find the side length here. This compares to the problems we were just doing in the previous section. We were working with 30, 60, 90 triangles and 45, 45, 90 and all that. Like it looks similar to that. However, we're not given that this is one of those friendly right triangles. Okay, this is just side length 5, and then this leg has a length of 12. You know, you could look into it and try and figure out if this is one of those special right triangles. But it turns out that it's not in this case. So, which of these formulas might be useful in trying to solve for that side length? Well, the one formula that we got that relates to the 3 side lengths of a right triangle is the Pythagorean identity, or the Pythagorean theorem. A squared plus b squared equals c squared. Looking at this picture, I'll call 5a and 12 can be b. The important thing is that c is the hypotenuse. So let's use the Pythagorean theorem. All right, so a squared plus b squared equals c squared. I want to substitute in the values that I have, solve for the one that I don't. So I'll have 5 squared plus 12 squared is equal to c squared. Simplifying, 25 plus 144 equals c squared. And adding these together, I get 169 is equal to c squared. All right, and then to finish this off, I'll want to take the square root of both sides of the equation. And I'll keep working over here since I'm kind of running out of room. Okay, and when we solve by taking square roots like this, it's kind of a tricky thing, but this, the square root of c squared, whenever we're taking the square root of something squared, this actually equals the absolute value of c, right? Because if c is a negative value, right, if c was a negative number, we would square it, it would become positive, and then you'd take the square root and you'd get back to the opposite of c, right? It's always going to be the positive version of c. And the way that this affects this equation that we're trying to solve is we'll get, yes, the square root of 169 on the left side, but we generally have a plus or minus. Root 169 is equal to c. However, sometimes when we're dealing with geometric problems or problems in trig, like we'll make a decision like which is it, plus or minus. In this case, since c represents the length of a hypotenuse, we're not interested in the negative value, okay? Really, we just want the positive value because for now, there's no such thing as a negative side length. Okay, so c is really equal to positive square root of 169, which happens to be a very nice number. This is just square root of 13. Okay, just applying the Pythagorean theorem, solving by taking square roots, and getting that length of the hypotenuse. All right, example 4, we want to find the perimeter of this parallelogram right here. Perimeter and also area. let's start with the perimeter because I think this is actually going to be the simpler one to find. The perimeter is just the length around the shape, whatever the shape is. If we're asked for the perimeter, it's just the distance that we would take to walk around this entire shape. And the values that we're given are, okay, this base right here is 8 units, and this diagonal, so this is like the other side, is 2 root 2. So the perimeter will just be the sum of those side lengths, which will be 8 plus 2 root 2 plus 8 plus 2 root 2. Okay, those last two terms were this 8 down here and this 2 root 2 over here. So we'll just simplify this. We'll have 16, that's adding the 8s together. What about 2 root 2 plus 2 root 2? That gives us 4 root 2. Okay, in case you want to see how that works, 2 root 2 plus 2 root 2. Sometimes I get questions about this. If we were adding together like 2x plus 2x, think of it like terms, right? We would add those two together and yeah, just add the coefficient and that will give you the sum. But what's really going on is like you could factor out the root 2. If you factor out root 2, you get 2 plus 2 on the inside, right? So then this is just root 2 times 4. But we're essentially combining these two like terms to get the 4 root 2 there. So just a little additional description there. Now simplifying from here, adding these two numbers together is not a simple task. If we wanted to give an exact answer, we could just use this as our answer, 16 plus 4 root 2 units squared. Or actually in this case, since it's a perimeter, it would just be units. But we could also add these together, and I just did it using my calculator, and I got approximately 21 point, maybe rounding to 2 decimal places, 6 units. Okay, so I'll just give this time. There are times where you'll be asked to provide an exact answer, so depending on what either I'm asking for in the problem or what your homework program is asking you for, you might give your answer in different forms. But in this case, I'm fine with this approximation. Okay, and this is units rather than units squared because a perimeter is not an area. Like the value for the perimeter is just the sum of all of these lengths, right? And adding up the lengths of a bunch of straight lines is just going to be measured in terms of, like if this was 8 inches, it would just be inches. But area, on the other hand, will be units squared. Let's get to that. So let's find the area. And the formula is base times height, where height is not this 2 root 2. It's not going to be that side length there. It's going to be this measure right here. So we want to find that height. So before we can actually find the area, we want to find the height. Okay, maybe think to yourself, what ideas do you have? How could we figure out what that side length is right there? Well, there are a couple marks on this indicating that these two side lengths are congruent. Okay, this means that we have an isosceles right triangle, 45, 45, 90. So to find this side length right here, I could just call it h, right, because it's the height. I know that h times the square root of 2 will give me the hypotenuse of this triangle. Okay, so over here, when I say find h, I want to solve this equation, h root 2 is equal to 2 root 2. Divide both sides by root 2, I get that h is equal to 2. All right, and my base is 8, so I can find the area now. A is equal to 8 times the height, which I found is 2. So I'm getting 16, and this is an area, so my units will be squared. Again, we're not told if this is inches or centimeters or millimeters or miles. So I'm just going to put units squared like that, just a little u squared, just to communicate to whoever is reading my work that I know what's going on here. I'm with the program. I know it's an area. So my units will be squared, whatever they are. So there it is. We have our perimeter and our area. Let's move on to circles. To find the area of a circle, all you need to know is its radius, where the radius is just the distance from the center of the circle to any point on the circle. Okay, and the center is defined as the point that is equidistant from all points on the circle. The area formula for a circle is A equals pi r squared. That probably sounds familiar. And the perimeter of a circle, it has a special name. We call it circumference. And the formula for circumference is 2 pi r. Okay, so the circumference and the area, to find that for a circle, all we need is the radius. Example 5, we're designing a deck for the backyard, and the deck will include a hole for a fire pit. This is a square fire pit, and a circular hole for a tree. So we have a diagram down here showing what this deck is going to look like, the shape, and the values, the measurements of some of the side lengths. How much decking board do you need for the project? Your answer should be measured in square feet. Okay, so the way I'm interpreting this is we want to find the area of this whole shape, but with the absence of this circle right here. This is where our tree is going to go. And we'll also have a gap over here for our rectangular fire pit. Okay, but we want to find the area of the rest of this. Okay, so yet another Home Depot problem. And I like these Home Depot problems because I feel like Home Depot is where a lot of people realize that they should have worked harder in geometry and trigonometry. I couldn't tell you how many times I've been standing in the lumber department trying to compute the tangent of some angle. Okay, so we want to find that area. First off, just our basic kind of approach, our strategy for finding that area. I have never seen this kind of shape before, so I certainly don't have a formula for it. However, I recognize this shape down here, right? Square, like I could find the area of a square. We also have the circle. I can find the area of a circle. The outside perimeter, like this large shape, is, you know, some kind of trapezoid or something, which I don't have a formula for currently. But if I just drop a perpendicular right here, I can divide this into a couple of more familiar shapes. All right, so I know that since these are both right angles over here and over here, when I drop a perpendicular from this side length, this is going to be a right angle. Okay, so then we have a square. And I can, the next thing, I haven't even written any work yet. I'm just sort of strategizing and trying to divide and conquer. That's sort of my strategy here. This long side over here, this is 20 feet, right? And the square that or rather the rectangle that I created over here by dropping this perpendicular has a length of 8 feet and a base of 11 feet. So I know that this distance right here, from here to over here, that's going to be also 11 feet. Okay, because with rectangles where we have 4 right angles, opposing sides are going to be equal to one another. Right, so some values that would be helpful to have is I'd like to know what this side is over here. Maybe I'll call this X. I would like to know what this side length is over here as well. Maybe I'll call that Z. Right, and this side length over here, I'll label Y, but we know that this is going to be 8. So my general strategy here is, how about we find the area of this entire region, right, disregarding the holes, and then we'll subtract the area of the holes, right? Because if I could find the area of this big shape and I could pretty quickly find the area of the missing shapes, I could just subtract those areas from the total area. So let's start by finding the area of this large shape. And I kind of hinted that I'm going to split this into 2 smaller shapes that are easier to find the area for: the rectangle on the right and the triangle on the left. Now, I labeled X, Y, and Z, those 3 sides of the triangle on the left, but since this is a right triangle, to find the area, all that I really need is, 1/2 base times height is the formula, so I just need this base, and the height is given by that value Y. Okay, so over here, and I guess I'll organize this by just the different areas. So I'll say area of the triangle A is 1/2 times the base times the height, which for our problem is 1/2 X times Y. Now pause for a second. I need X and I need to find Y, okay? So Y is pretty quick, right? So I'll say note Y is equal to 8 feet because, this opposite side of this rectangle is equal to 8. And X, how am I going to find X? Well, I know that X plus 11 feet is going to add up to the entire side length of 20 feet. So X plus 11 is equal to 20. I can just subtract 11 from both sides. X is equal to 9 feet. Okay, so now there's that, there's that. So now let's pick back up. So the area of the triangle, which is what I'm working on here, area is going to be 1/2 9 feet times 8 feet. All right, so yeah, and by the way, X is 9, Y is 8. Notice that this picture is not drawn to scale, and that's very common. All the time you'll see problems where the image is not drawn to scale, so don't get too scared if you see that, hey, X looks like it should be smaller than Y or something like that. Trust the math over the picture. That's my advice. All right, so this will be 1/2, multiplying, you know what? Let's just do 9 times 4, right? Because 8 divided by 2 is 4. 9 times 4 gives us 36. And the units are going to be square feet, right? Because we multiplied feet times feet. So this is the area of the triangle. So maybe I'll denote it, area triangle. And I'll put a little cloud around this because this is something that I'll need eventually. Good, now that we have the area of the triangle, let's find the area of the rectangle. area of, this time, the rectangle. And this one's pretty straightforward. Area of rectangle is just equal to base times height. And for this one, we know that the base is 11 feet times the height, which is 8 feet. So I have 88 square feet for the area of the rectangle. I'll put another little cloud around that. So those are like the positive values, right? Now let's find the area of the small square and of the circle. Okay, for the square, area of square. Again, this is just a rectangle, except the base and height are equal. In this case, it's equal to 1.8 feet. So the area of a square is really just like, base squared, we could use. All right, and that value is 1.8 feet. And we're going to square that. 1.8 squared, I am getting 3.24. And the units are also going to get squared, so we'll have square feet again. There's our area for the square. Maybe I'll circle this or I'll put a little red cloud around this because this is one of the negative areas that we're going to subtract. And the last one, let me put up a little divide here so I can keep working up here. Now let's find the area of the circle. The circular hole for our tree. And the dimension that's given here, that's marked right here, this is not a radius, but this is a diameter. Now remember, the formula for the area of a circle, so area of a circle is equal to pi r squared. So we'll want to find the radius, but the relationship between the radius and the diameter is very simple. Radius is just equal to 1/2 the diameter, which in this case will be 1/2 times 2 feet, which will just be 1 foot. Very nice. So then the area of the circle is going to be pi r squared. Pi times 1 squared is just going to be pi square feet. And this is another negative area. Whoops, I meant to do that in red. So now finally, with all of that taken care of, I can say, let's find the area of the deck. Okay, so I'll just call this A. And remember, our strategy is the positive area is going to be the area of the triangle plus the area of the rectangle. And we're going to subtract from that the area of the square and the area of the circle. So let me substitute in these values. The area of the triangle, I got 36 feet squared. I'll do the units at the very end, and then plus 88 for the rectangle, and we want to subtract from that 3.24 plus pi. Okay, and this whole entire thing is going to be measured with units square feet. Okay, so now I'll use my calculator. And at this point, I'm going to introduce the approximation sign, because over here, when I do 3.24 plus pi is an irrational number, meaning that the decimal just goes on forever and never stops. I'm going to round at this step. And I'll just round to, how about 2 decimal places? I think that's reasonable given that this other value we found for the area of the square ended up being, 2 decimal places. So adding these two together, I get approximately 6.38. Okay, and then 36 plus 88, I'm getting 124. Keeping my units there. All right, and then let's do 124 minus 6.38. Taking that difference, I get 117.62 square feet. Okay, and I'm thinking that's my answer. Just looking back to the problem to make sure, I like to go back and check and just make sure I'm actually answering the right question, not ending too soon. Sometimes I find students putting boxes around answers when really it's, they just found the area of the triangle and they forgot that there's much more to the problem. But we were just asked to find how much decking board do we need for the project, answering this question using units of feet squared, and that's what we ended up with. So here's our answer. So I'll just say we need approximately okay, and I use this approximately because this is technically a rounded number that we get. Approximately 117.62 square feet of decking. And I will box that up. Okay, I like this problem a lot. This is a great one to study from. We've got a bunch of different area formulas that we employed. We had to use some geometric reasoning here, splitting up this area, the big area into multiple shapes, namely that right triangle and that square, and then subtracting the negative area. This is a great practice problem. You'll see problems similar to this on the homework and probably on quizzes and tests as well. But that brings us to the end of this section on perimeter and area. Section 1.5, we're going to move into 3-dimensional objects, and we'll talk about volume and surface area. So I will see you in that next video.